When we talk about filters, so you know that a filter is a kind of a system, right? So here we are interested in LTI systems. Of course, our analysis mostly is related to the linear time invariant systems. So filter or system can be analogously used. The terms the filter or a system, we can use it analogously. So by definition, what do you understand with a filter is it's nothing but a system which will allow certain frequencies to pass through and stop some of the frequencies, or it's rather used for filtering some kinds of signals, or let's say you're removing some noise, some undesirable noise in a signal. That is also a kind of filtering. So in general, the definition of a filter is this only, for filtering unwanted components in a signal, you can say in general. But now when we are talking about designing a filter, we are talking about an LTI system in general. So the filter that we are going to, so when I say a filter or the LTI system, it's the same. That's what I mean to say. So depending on the kind of application the system is going to be used, okay, it can be given different names. So the filter that we are going to be learning how to design can be used for various purposes. Like the very first one I will say is for removal of noise, undesired noise in a signal. So some sort of frequency selective operation is what we are doing here. Okay, that's one thing, or the definition which you generally know what it is. Other than this, the system or the filter we design can be used for spectral analysis. So if there is some kind of spectral analysis of the signals that need to be performed, okay, we can make use of filters, right? And then it can be used for signal detection and various other purposes in, let us say, your communication systems or your radar and sonar systems. Okay, in all such kind of systems also, there could be some sort of signal analysis or some signal detection that you are performing. So here also we make use of these filters. Okay, then you could be performing some spectral shaping. Okay, so when I talk about spectral shaping, maybe the spectrum of a particular signal, you want to change it in a desired fashion. Okay, in that case also we can make use of filter. So as we are talking about everything being spectral, you can see that we are analyzing the signal in the frequency domain. Okay, so most of the filters that we write, or even the frequency response of the filter when we write, see, usually whenever we are designing a filter, the desired frequency response of a filter will be given to you. And based on that, we are going to design the filter. What is this frequency response? How do you want the characteristics of the filter to be in the frequency domain? Okay, so in the frequency domain, how do you want the filter to be? Now, say for example, an ideal low pass filter. If I consider an ideal low pass filter, so what does a low pass filter do? It will pass the low frequency components, whereas stop the high frequency components, right? It's going to have a cutoff frequency. Until then, it's going to pass all the frequency components. So how is the frequency response of the filter going to be? It needs to be straight or constant in the pass band is what we call. So this pass band is where the frequency components are passed through, and then this is the cutoff frequency until where all the frequency components are passed, and then beyond your omega c or the cutoff frequency, we want all the frequency components to be cut off. So this is a low pass filter. Okay, this is a low pass filter which passes all the low frequency components. What I intend to tell you here is this characteristics of a low pass filter which is given to you is called as the frequency response of the filter. So we are specifying how we want the filter to be in the frequency domain. Okay, why frequency domain? Because we are interested in filtering out certain frequency components. So this you have to do it in the frequency domain. We cannot do it in the time domain. Okay, because time domain, you will not have any idea of what the frequency components are present in the signal. So the frequency response of the system, which is defined in the frequency domain, will be specified to you. Okay, and you have to go about designing this filter so that it matches the given specifications. Whatever the specifications is given to you, it is going to match this given specifications. So that is our aim. So again, let us get back to the system. Let's get back to a system. So we have an LTI system with us. We have an LTI system. So what do we usually do? We give an input to the system, x of n, and we find the output of the system, y of n. So you know y of n is given as x of n. So h of n, or the impulse response of the system, is what we know, and the output is simply the x of n convolved with h of n. So when I say we are designing a system, we are interested in designing a system, what is it that we are interested in finding out? So we are interested in finding out the impulse response of the system. So far in the problems that were given to you, the impulse response was given and the input was given. So you were just finding the output of the system. Okay, so you didn't bother about what this h of n has to be or how it has to be. Okay, according to some system which is given, you've just found the output of a system. But now we are interested in designing this impulse response of the system, that is the h of n of the system. How do you design? Based on your specifications that is given to you. Based on the specifications that are given to you in designing h of n, okay, or the impulse response. The same thing in the frequency domain. How do we write this? How do we write this expression in the frequency domain? Y of omega is x of omega into h of omega. Right? This is the frequency domain representation. You know this. We have applied DTFT here. Okay, we have applied DTFT and written the equivalent expression for convolution in the frequency domain. So what is it that you are interested here now? To find what is this h of omega. H of omega. So this frequency response which I wrote here for a low pass filter, right? This is nothing but h of omega. This is the desired frequency response or which you have to design. So what is it that you're going to find out? We are going to find out the filter coefficients. What do we mean by filter coefficients? The values of this impulse response of the system h of n. See, they are related, right? Whether you're finding h of n or h of omega, they are related. Either you find h of n, you can write down h of omega, or from h of omega, you can write down h of n. Everything has a representation and they are all related, correct? So when we say filter coefficients, we are interested in designing this h of n or the h of omega. So that is what is the frequency response of the system. What is the frequency response of the system? H of omega is called as the frequency response of the system. Let me write it here. So h of omega is called as the frequency response of a system. H of n is what? It is the impulse response of a system. So if you take the DTFT of h of n, right, we are going to get h of omega. That is the frequency response of the filter. On the other hand, if you write the Z transform of h of n of the impulse response, what do you get? You get h of z, and this is called as the transfer function of the system. This is called as the transfer function of a system. So you see all these are related. Okay, h of n, DTFT, Z transform, that is the transfer function, all of them are related. So when we are designing, we can design any one of them. See, again, it depends on the kind of method you're using for designing. The filter design method that we are using for the designing purpose. Based on that, we either design h of n or h of omega or h of z. Anything you design, it's finally the filter that you are trying to find out. can convert one from the other. We can convert one from the other. Okay, so I hope the point is clear to all of you. So the purpose of filter design is to find the impulse response of the system, or the frequency response of the system, or the transfer function of the system. So that is what we are trying to find out. So what are the kinds of filters that we are interested in designing here? So basically there are two kinds of filters that we will be designing. They are called as IIR filters and FIR filters. So what does IIR stand for? Infinite impulse response filter. Okay. FIR stands for finite impulse response filter. Finite impulse response filter. So these are the two kinds of filters which we are interested in designing. So what are these FIR and IIR filters? So now we know the formula for convolution, right? So what is that? Y of n is summation h of k, x of n minus k, k from minus infinity to plus infinity. So why am I talking about convolution? Because we are trying to find the output, and you can relate the impulse response to the input and output using the convolution equation, right? Now, if the impulse response of is finite, it's of finite duration, then we call it as a FIR filter or a finite impulse response filter. On the other hand, if the impulse response of the filter is of infinite duration, then we call it as an IIR filter or an infinite impulse response filter. Okay, so that's the major difference between the two. So there'll be finite number of samples in the FIR filter, whereas infinite number of samples in the IIR filter. Whatever said and done, both the filters we want it to be causal. Okay, we are interested in designing causal filters because we don't want non-causal or anti-causal filters, because anti-causal filters are predictive in nature. You have to predict what the future is going to be in that. You know the difference, right, between causal and anti-causal. Anti-causal depends on future inputs as well. So that we don't want to actually design. We are interested here. It's not that we don't have anti-causal filters, but here we are not interested in designing anti-causal. We are just interested in designing causal or predictive filters. Okay, so we don't have to. So what happens to this lower limit? It becomes 0, right? Why? Because you know h of n will be 0 for n less than 0. This is the condition for causality. You have to go back to your impulse response characteristics which we had discussed. Okay, so the impulse response of a system will be 0 for n less than 0. So that means the system is causal, right? That means the system is causal. So what happens to the equation here will be summation k 0 to infinity h of k x of n minus k. So this is an IIR filter. Why it's IIR? Because see, your upper limit is infinity. So h of n has infinite number of samples. On the other hand, an FIR filter, y of n will be summation k 0 to m minus 1. That means there are finite number of samples in this filter. Let's say m samples you have in the impulse response of an FIR filter, x of n minus k. So this is an FIR filter that we are talking about. It has finite number of samples in its impulse response. So we need to find what is this h of k in case of IIR and FIR filters. So this is also the difference equation representation of a filter in general, right? Why difference equation? Because you are relating x of n and y of n here. You could also have terms y of n minus 1, y of n minus 2 and all that. We have written the difference equation before, right? So difference equation is one characteristic or representation of a system where you're relating the input and the output. Is that clear? Now there are some more differences between an IAR and FIR filter. So what are those differences? First of all, the IAR filter is a kind of filter which is also called as a recursive filter. Okay, so shall I put it here only under this comparison so that it will be easier to write down. So that's the equation for IAR and FIR. IAR is a recursive filter. So recursive filters are those which depend on past outputs also. Which depends on past outputs also. Input it is going to depend. It's going to depend on x of n and past input values, but it also depends on past output values. Okay, let me just write that in the form of an equation here. So you have the equations or the convolution equation for that we have. Now what is a recursive system? Okay, IAR is a recursive system or a recursive filter. So what is a recursive filter? The output of a recursive filter will be a function of x of n minus 1 and all these values. That is your input and past inputs. Also, it will depend on the past output values also, like y of n minus 1, y of n minus 2 and all these things. Such a system is called as a recursive system. Whereas your FIR filter is a non-recursive system. Okay, FIR's filter is a system. So a non-recursive system, the output is going to be a function of input and past inputs and not of past outputs. You will not have past outputs in case of the non-recursive systems. These terms will be missing in case of non-recursive systems, which are also the FIR systems. Is that clear for everyone? So IAR is a recursive system, whereas FIR is a non-recursive kind of a system. So that is one more difference between IAR and FIR. Then, when we write down the transfer function of a system, so you know that there are poles and zeros of a system, right? Whenever you write the transfer function. So the IAR filter is one which has both poles and zeros. IAR filter has both poles and zeros. Whereas your FIR filter consists of only zeros. It will not have poles in it. Okay, the FIR filter has only zeros. There are no poles in the FIR filter. So when you write the transfer function of an FIR filter, it will have only the numerator polynomial. It will not have the denominator polynomial, the FIR filter. So since the stability of a system is related to the poles of a transfer function, you can relate the stability of a system to the poles of the transfer function. And if all the poles lie within the unit circle, okay, then we say the system is stable. So IAR filter may or may not be stable depending on the location of poles. It may or may not be stable depending on the location of the poles. Whereas an FIR filter is always stable. Okay, it is always stable because there are no poles itself in the transfer function. So the location of poles doesn't matter. So since there are no poles, it's always a stable system, an FIR filter. Okay, so these are some of the differences. We have more of them, but as we go on, discussing both the filter design structures, you will get to know more and more of these. And one more point I will just mention regarding to a linear phase. an FIR filter always has a linear phase response. Linear phase response. Whereas an IAR filter may or may not have a linear phase. It is generally not possible to have a linear phase response in IAR filter. What do I mean by saying a linear phase response? Okay, so now if you look at the frequency response of a filter, that is what we'll design, right? H of omega is what we are going to design. So H of omega, the expression for H of omega can be written as we wrote it here itself. Okay, so H of omega, or the frequency response of a filter, it is a complex domain, right? So therefore we can write it as a magnitude and phase component, like generally how we write the complex numbers. So H of omega can be written as C e power minus j omega alpha, that is there. This is one frequency response of a filter. It's actually a low pass filter frequency response. So how do we get that? We will see. So wherein the C represents the magnitude response of the filter and minus omega alpha is the phase response. So if I represent phase by phi, so phi of omega is minus omega alpha. That is the phase response. So isn't this phase response a linear one? It is varying linearly, right? Omega is varying linearly in this case. So minus alpha is the slope of the line. Minus alpha is the slope of the line. So such kind of characteristics we obtain only for an FIR filter and not for an IAR filter. Magnitude response you can obtain for both, the way in which it is desired. But the phase response is going to be linear for an FIR filter, but not linear for an IAR filter. Someone's unmuted. Okay. I hope that's clear. Yeah. So as we go on, designing or learning the different techniques for designing these filters, things will be more clear to you. So don't worry too much. At the end of it, once we have learned both the filter designs, okay, it will be better. The difference will be much more clear. Yeah, so what is it that you're going to be learning in your syllabus is, just write it here only. So in case of IAR filter, how we design the filter? Okay, first of all, what kind of filter is the one that we are designing? Whether it's IAR or FIR, we are interested in designing digital filters. Okay, so this is our aim. That is why I wrote H of n there. Okay, we are interested in designing digital filters because obviously we are talking about digital signal processing. So all those tools that we discussed are for digital signal processing, and now the filters or the systems that we are interested in designing are also digital in nature. Okay, so we are interested in designing digital filters. Or the method in which we design a digital FIR filter is called as the window technique. I'll just mention the techniques here. Okay, don't worry too much. We'll take each one of them and understand how to do it. So FIR filters is designed using the window technique, and we have one more method called as the frequency sampling method. So using these two methods, we are going to be designing the FIR filter. Then IAR filter, in IAR filter, actually we first design the analog filter. The analog IAR filter is designed first, and then transformations are applied to this analog filter. Okay, one popular transformation is called as bilinear transformation, BLT for short, and then the digital filters are going to be obtained. Okay, so in IAR filter, we first design the analog IAR filter and then apply transformations called as bilinear transformation to obtain a digital filter. Two kinds of IR filters we'll be learning. One is the Butterworth filter. Okay, Butterworth filter and Chebyshev filter. Two kinds of IR filters are there, Butterworth and Chebyshev. So all this, consists of your module 3 and 4, wherein we'll be designing with these different techniques. Also, after you have designed the filter, we will also draw the structures for these two kinds of filters. So what are structures? A way of representing a system. Equation is one way, that is mathematically representing. Structures is using adders, subtractors, multipliers, all that. Pictorially, how you represent a system. That is nothing but a structure. So for both these IR and FIR, we'll be learning how to draw these different structures. Okay, so that's an overview of the filter design part of your syllabus that you're going to be learning. So first we have to start with the FIR filter design, cover its structures, and then move on to IR filter design, and then cover the structures of the IR filter design. Okay. Yeah, so we'll just do a very small topic in your FIR filter design. FIR filter design or finite impulse response filter design. So like I told you, a very important characteristic of an FIR filter is its linear phase response. Okay. An FIR filter has a linear phase response. So once you have the frequency response of a filter, if you plot the magnitude response and the phase response will be linear. If I have to just give you an example, let us say your magnitude response h of omega, okay, I'll put the magnitude to indicate it is the magnitude response, could be something like this. Let's say it's a low pass filter and it is something like this. This is the magnitude response. Whereas your phase response phi of omega, let's write, okay, will be linear. I'm sorry about that. Okay. So it's going to be linear and having a negative slope. To be very precise into what you're going to get, we get a negative slope but a linear phase. So see, in this interval from say minus omega c, between the cutoff frequency, to plus omega c, the phase response of an FIR filter is going to be linear. This may not be the case with the IR filter. So that is why in applications which requires a linear phase, why we need a linear phase? So that there is no phase distortion. Okay. In applications where the phase distortion is not tolerable, in such kind of applications we go in for the FIR filter. Okay, because it does not distort the phase. Whereas if the phase distortion is tolerable in some of the applications, we can just make use of an IR filter. Again, it depends on the application that you are trying to use. Okay, so that's how the FIR filter is going to be. Now, this linear phase characteristic of an FIR filter happens because of one important property of the impulse response. Okay, because of one important property of the impulse response of the system h of n, this linear phase is possible. So what is that? The impulse response of the system will be symmetric, or anti-symmetric. Okay, So what are we talking about here? We're talking about the impulse response of this system. So the impulse response, the values that you find out, if that signal is symmetric or it's anti-symmetric in nature, then this linear phase response property is possible. Suppose it is not symmetric, then we don't get a linear phase response for a filter. So the impulse response of an FIR filter will be symmetric or anti-symmetric in nature. You know what is symmetric and anti-symmetric. What is symmetric? The even signal is nothing but it is symmetric. Anti-symmetry is the odd signal. All signals need not have to be symmetric or anti-symmetric, right? You have signals which don't fall into this category also, right? So those signals which are either symmetric or anti-symmetric, that is the impulse response. If it is symmetric or anti-symmetric, then automatically this linear phase response characteristics is going to be satisfied. Okay, so that's an important property of an FIR filter. So when we say symmetric, okay, symmetric about the origin is what we had seen before. Now the symmetry is about the midpoint of the circle. The symmetry or the anti-symmetry. Once I say symmetry, the same thing holds good for anti-symmetry. Okay, so the signal or the impulse response of the system will be symmetric about the midpoint of the signal, because your h of n here has a finite number of samples, isn't it? So that is the definition of your FIR filter, finite impulse response filter. It has a finite number of samples in it. So it has m samples in the impulse response of the filter. So if we write the equation we wrote, right, the y of n equation which we wrote using the convolution will be summation k from 0 to capital M minus 1 h of k x of n minus k. It has m samples in its output, in the impulse response, and it is symmetric about the midpoint. So if it is symmetric about the midpoint, how we write the equation is h of n will be equal to h of m minus 1 minus n. Okay, this is the condition for symmetry, for the signal to be symmetric. Okay, so if the impulse response of the system is symmetric in nature, or if it is anti-symmetric, when will it be anti-symmetric? When h of n is minus h of m minus 1 minus n. This is the condition for anti-symmetry. Anti-symmetric. Okay. How were we writing the equations in general now for signals? How were we writing? If x of minus n is equal to x of n, that is symmetric. X of minus n is equal to minus x of n, that is anti-symmetric. So this is about the origin that we were writing. Now what I am telling you is we have samples from 0 to m minus 1. In that, about the midpoint, that is m minus 1 by 2. About this point, the signal is symmetric. So the equation obviously will change. It will not be the same as this, what we had written. So these two equations which we have written here are the conditions for the signal to be symmetric or anti-symmetric. Okay. Now the point here is what we have to do now. We know that if the impulse response of the filter is symmetric, then we get a linear phase response. So now we have to derive the equation for the frequency response of the FIR filter. We have to derive the equation for the frequency response of an FIR filter. So that we have to do now. So what we can do is we can first take the impulse response, take the Z transform of the impulse response. So that is, we write the transfer function of the filter and then convert that to frequency response. So I will tell you how to convert it to frequency response. So before we move ahead and write down the expression for the frequency response of the filter, let us draw this signal first and see how the signal looks like so that it's useful for our derivation. Okay. So how will this signal look like? the symmetric function. Okay, so I am trying to draw h of n now for it being symmetric. Antisymmetric, of course, the same thing holds good. So first let's discuss the stuff for symmetry. So it has m samples in it, right? So your value of m can be odd or even. That possibility is there, right? So if your m is even, there are even number of samples in your h of n. Then how does the signal look like? Okay, that's what I'm trying to draw. So the first sample is at 0, the last sample is m minus 1. So we have total of m samples in the impulse response of this filter. So let's say the first sample and this sample is like this. Okay. So we are going to have many such samples. I will not draw all of them, just for our convenience. I'm drawing these many samples. Just one example I've taken. So isn't this symmetric? The signal is symmetric. About which point? About the midpoint. So what is this point? M minus 1 by 2. M minus 1 by 2. So we have 8 samples total here, right? M is equal to 8. 0, 1, 2, 3, 4, 5, 6 and 7. That is how it is. So what is the midpoint of this? Midpoint will be at the value 3.5. At the value 3.5, because you don't have a sample at the center. Since m is even, we don't have a sample at the center. Correct? So this is how the signal will look like. Then when m is odd, how will the signal look like? So why am I drawing this? Is because I need this for the derivation of my frequency response. So now you have a sample at m minus 1 by 2 at the center, exactly at the center, because this is m is odd here, and you will have equal number of samples on either side. Equal number of samples on either side of the signal. So that's the case when m is odd. When m is odd, that is how the signal looks like. So do you want to check using the equation whether this is satisfying? So just see the equation now. The first equation, h of n equals h of m minus 1 minus n. So the first sample, h of 0, will be equal to h of m minus 1, isn't it? If you put n is equal to 0, in the same fashion, the corresponding values are going to be equal. So that is the reason the equation is going to change, because here the symmetry is about the midpoint and not about the origin. Okay. So once we have written this, now both for m even and m odd, we'll have to derive the frequency response of an FIR filter. We have to derive the frequency response of an FIR filter. So let's do that. So first let me consider the case for m even. For m even, I hope you have taken down this case, or we'll draw this once again later, m odd. I'll just take m even now and derive the frequency response of the filter. Yeah. So h of n is the frequency response of the filter. Let's write down the Z transform of h of n. Z transform of h of n. So by definition, what is that? H of z is the transfer function or the Z transform of h of n. So if you write the equation for that, n from 0 to m minus 1, h of n z to the power minus n. H of n has samples from 0 to m minus 1. Therefore, the summation also is from 0 to m minus 1. So we are deriving this case for m even. For this particular signal which we have written for m even, we are deriving this case. Okay. Now I want to split the summation into half each. That is n from 0 to the first half of the samples. These half of the samples into the first summation and the second half into the second summation. Okay, so if I have to do that, I obviously need to know what is the index here and what is the index at this point, isn't it? So let me just write what these index values are. Yeah. So if this is a center at m minus 1 by 2, this is your center, what will be the sample or what will be the index at this point? Isn't it m minus 1 by 2 plus half? Yes, you're going to get this value. So what is that? M by 2. So this index is m by 2. The second portion of the sample that is starting. Then what is the index before m minus 1 by 2? M minus 1 by 2 value, you have it here. Okay, it is to the left by half value. So minus half. Minus half. So what is this? M by 2 minus half is a minus 1. Is a minus 1. So m by 2 minus 1. M by 2 minus 1. Why did I write down that index? Because I want to split this summation into two portions. The first portion will have the first half samples. The second portion will have the second half samples. So what is the index here? M by 2 minus 1 in the first half. H of n. Z bar minus n. Plus the second summation will start from m by 2 up to m minus 1. The last sample. H of n z to the power minus n. Z to the power minus n. Okay. Then in the second summation, I want to substitute n to be m minus 1 minus small m. Capital M minus 1 minus small m. So how are the limits going to change? Okay, the limits. So if n equals m by 2, right, what will be m? Small m is m minus 1 minus m by 2. So that is m by 2 minus 1. M by 2 minus 1. Upper limit, if you put n equals m minus 1, then your small m is 0. Small m is 0. So let us substitute that here now. So the first one, n0 to m by 2 minus 1, h of n, z to the power minus n, m from, the limits are from m by 2 minus 1 to 0. Or I can just write it as 0 to m by 2 minus 1 since it is a summation. Then h of m minus 1 minus m, z bar minus of m minus 1 minus m. We have substituted for n there. Okay. Now, as usual, what do? We don't want to keep m as our variable here. We want n, right? Which we can do it because it's just a variable and can be written as n. So that I have written here. Okay. Okay. Yeah. Now, what is h of n? The condition for the symmetry. we know that h of n is equal to h of m minus 1 minus n, isn't it? So what will be this value? Summation n0 to m by 2 minus 1 h of n z to the power minus n plus summation n0 to m by 2 minus 1. Here I am going to substitute as h of n because this condition of symmetry is satisfied for an FIR filter. So in place of h of m minus 1 minus n, we are going to put h of n z power minus of m minus 1 minus n. Okay, so now let's combine both the summations, because the summation is same between m by 2 minus 1, h of n is common, and we have z power minus n plus z power minus of m minus 1 minus n by combining the two summations. So this is what h of z. This is h of z. Okay, that is h of z. So from this h of z, we have to next write down the frequency response of the filter. We have to write down the frequency response of the filter. Now we can obtain the frequency response of the filter, okay, using the transfer function. So there is a relationship between the Z transform and the DTFT of a signal. Okay. So what is that relationship, or how do you obtain the frequency response? Or the frequency response is nothing but what? The DTFT, okay, of a signal using the Z transform. So in the h of z, we can make a substitution. Z is equal to e to the power j omega. Z is equal to e to the power j omega, so that we can obtain the frequency response using this. So how do we get this relationship? It's quite obvious. What is your h of z, or the general formula for h of z is h of n z to the power minus n, right? This is your Z transform of the sequence h of n. So now if you make the substitution z equals e power j omega, what is it that you get? H of e power j omega summation n minus infinity to plus infinity h of n e power minus j omega n. Okay, so isn't this your DTFT formula? Yes, this is your DTFT formula. So using the Z transform, we can obtain the DTFT. What is the relationship? This is the relationship. Z equals e to the power j omega. Okay, so in h of z, let us now substitute z equals e power j omega. Okay, let me erase this. So if we put z equals e power j omega, h of e to the power j omega will be summation n0 to m by 2 minus 1 m by 2 minus 1 h of n z is what? E power j omega, and we have minus n in the power, plus e power j omega minus of m minus 1 minus n. So we have substituted for Z. So this is nothing but the DTFT of the signal, or in turn we call it as the frequency response. Just write it here, frequency response of a system. Frequency response of a system. Okay. Now let's simplify this a little bit. Okay. Though we can leave it at this point, your h of e power j omega is a complex quantity. The frequency response is complex. So how do we generally plot the frequency response? We have to plot the magnitude response and the phase response. That's how we have been doing in all your DTFT tools or FT tools or frequency Fourier series tools and all that. Okay. So we have to find the magnitude response and the phase response of the filter. So we have to obviously separate this out in the rectangular form or in the polar form. Okay. So here we can see that the polar form of representation will be much easier for us to do. Okay. So how do we get the magnitude and the phase response from this equation? So we have to simplify that a little bit. So what we'll do here is, so I'll just keep the summation as it is, -1, h of n also as it is. So in this exponential term, let us take e power minus j omega into m minus 1 by 2 as a common factor. Okay, or rather you can say multiply and divide by this term, whatever is convenient or is understandable. So e power minus j omega n we have here. So if I have to take this term common, I should have a term e power plus j omega into m minus 1 by 2. Am I right? So then when you again multiply it back, you will get back this term. When you multiply these two terms. Okay, plus for the second term, we already have an m minus 1 term here. So in that, half of it you are removing outside, right? Half of it is taken out. So what remains here is e to the power. Okay, so let me write this as j omega n. I'm separating out the terms here. So e power plus j omega n you have, and e power minus j omega into m minus 1 by 2. Into m minus 1 by 2. So now check, if you multiply these two terms, you get e power minus j omega into m minus 1. Into m minus 1. Okay, I hope that is fine for everyone. So why are we doing this? Because we want to write this in the polar form. So that's the reason we are going to write it in this way. Okay, now so let's just combine all these exponential terms and write it as, okay, so summation n0 to m by 2 minus 1 h of n e power minus j omega into m minus 1 by 2. This term, I'll just keep it as it is. Now let's combine all the exponential terms here. So we are going to write this as e to the power minus j omega. I'll take it common in the first term. Okay. Minus j omega. So if I take minus j omega, I have an n here and minus of m minus 1 by 2 in this term. So the first term, if I combine, okay, plus the second term, let us take e to the power plus j omega common. Okay, so if I do that, I have n minus of m minus 1 by 2. So there are obvious reasons why I am writing it in this fashion. Okay, if you have guessed it by now, the exponential term in the bracket can be written as a cost term, right? So that's the reason we are doing it in this way. Okay, so what is the term in the bracket? So we have summation n0 to m by 2 minus 1 h of n e power minus j omega into m minus 1 by 2. This is one thing. What is in the bracket? It is nothing but 2 cos of omega into n minus of m minus 1 by 2. Cos of this angle. 2 times cos of this. Is that fine? Okay, so the reason for simplifying it is to write it in the polar form first of all, so that we can separate out the magnitude term and the phase term. So when you're doing that, you should also make sure that these terms in the bracket, the exponential terms that we have, should be written in some real form. Okay, so either it is cos or sine. So that is how it turns out to be cos here. Okay, then. So this term does not have an n in it. So we can write this term outside the summation. We can write that term outside the summation. So that will be e power minus j omega into m minus 1 by 2. Writing it outside. The remaining term, summation n0 to m by 2 minus 1 to h of n, cos of omega into n minus of m minus 1 by 2. Okay, so this is what h of e power j omega, or the frequency response of the filter. The frequency response of the filter. So now, haven't we written this in the polar form? How is it? The polar form, see here, this term is the magnitude term and this term in the power of the exponential is the phase term. Because what is the formula or the frequency response, if I have to write it in the polar form, magnitude of h of omega into e power j phi of omega, r e power j theta. Okay, that's the polar form. So this gives you the magnitude of the complex term and this gives you the phase. So compare this equation and this equation that we have derived. So what is the magnitude? What is the magnitude of h of omega? Yeah, h of omega or h of e power j omega we write. So let me write it as h of e power j omega. So what is the magnitude here? Summation n0 to m by 2 minus 1 to h of n cos of omega into n minus of m minus 1 by 2. That is the magnitude. And what is the phase? The phase is nothing but, minus of, it is j omega, right? I mean the j and the phi of omega, the remaining term. So what's remaining there? Minus omega into m minus 1 by 2. Minus omega into m minus 1 by 2. That is your phase. So if you look at the equation of the phase response, isn't this a linear function? Yes, it's a linear function, right? It will be a linear graph. What is the slope of this graph? Minus of m minus 1 by 2. It has a negative slope. So it's a linear waveform with a negative slope. So we get a linear phase response for an FIR filter because the impulse response, h of n of the filter, we assumed it to be symmetric. Even for antisymmetric, we will get a linear phase. So we can do the derivation for antisymmetric also in the same fashion. Okay, and then m is called as the order of the filter. So that m actually indicates the number of samples you have in h of n, right? And also the maximum past inputs that you can consider. That is indicated by the order of the filter m. So m stands for the order of the filter. So usually FIR filters have a higher order compared to IAR. Okay, IAR filters have a lesser order, whereas FIR filters, the order of the filter will be very high. The number will be quite high for an FIR filter. So is this point clear? Okay. One more thing. Now suppose this term that we are writing here, this magnitude term that we have written here, possibilities are there that this value can be negative. For certain values of omega, this value could be negative. It is not a magnitude as such that we are writing it here. Okay, it's just r e power j theta form which we have derived. So it's not a magnitude as such. You can ask me that it could be a positive number always, need not be, right? Because your cos value can be negative sometimes. So there could be values of omega for which this term could become negative. See, even though we are calling it the magnitude, I hope you're getting my point. From this equation, what we have derived from this equation, okay, so from this equation, what is it that we have derived? We have written it in the form r e to the power j theta, r e to the power j theta. So r, we call it as the magnitude, but it is not absolute value. Okay, it's not the absolute value that we are talking about. So it could be possible that this magnitude function could be negative. So that is why we don't represent this with the magnitude like this or the absolute value like this. We write it as HR of to indicate omega. So if your HR of omega is positive, that is greater than 0, then this is the phase value. Now suppose your HR of omega is negative. If your HR of omega is negative, let's say, okay, so you'll have a -1 here, right? We'll have a -1 here. So how do we account for this -1 is the question. So what we can do is, can we write -1 as e to the power j pi? Yes, -1 can be written as e to the power j pi. So e to the power j pi. So when HR of omega is less than 0, when it is negative, so that negative sign, that -1 can be written as e power of j pi. So once you have e to the power j pi here, we can combine this e power j pi with this e to the power j phi of omega, isn't it? So what happens to the power? It will get added. So your phase response will be minus omega into m-1/2 plus pi. So why did you get this plus pi? Because your HR of omega term could be negative. So if it is negative, that -1 can be written in terms of exponential as e to the power j pi. So once you write an exponential here, you cannot have this exponential term with HR of omega. You'll have to shift it to the phase term. E to the power j pi should be shifted to the phase term because it is r e power j theta form. So phi of omega plus pi, it's going to become phi of omega plus this term pi. So that's the reason why your phase response will become minus omega into m-1/2 plus pi when your HR of omega is less than 0. Okay. So that is the expression for the frequency response of a filter, FIR filter, when M is even. We have derived this for, I'm sorry. So we have derived this for M being even, right? So whenever you're designing your filter, the filter specifications will be given to you, okay? And based on the technique that we are using, we are going to be designing this h of n, the impulse response of the filter. You will get values for this h of n. So once you do that, they can also ask you the frequency response of the filter. Okay, so if they ask you the frequency response of the filter, then using these values of h of n, you will have to substitute it in this equation of HR of omega. and phi of omega, and write the magnitude and the phase response. Okay, whatever might be the technique that we find h of n. For an FIR filter, it is called as the window technique. Using the window technique, we find the h of n values, the impulse response of the filter. Once you have found that out, you will also know the order of the filter. Okay, so either for m even or for m odd, in that corresponding equation of the frequency response, you'll have to substitute the values of h of n and write down what is the frequency response, that is the magnitude response and the phase response. Okay, is that clear? So in the same fashion, we'll have to derive the expression for m being odd. Derive the expression for the frequency response when m is odd. Okay. So now we'll have to derive the frequency response for a symmetric FIR filter when the order, that is m, is odd. Okay, so let's do that derivation now. So when m is odd and we are talking about a symmetric impulse response. Okay, symmetric h of n, I'll write. So a symmetric h of n when n is odd will look something like this. So it should have a total of m samples in it. So the first sample starts at 0 and the last sample is at m minus 1. The impulse response is symmetric about the midpoint. Okay, it is symmetric about the midpoint. So m is odd. Let me take a value of m to be equal to 9, let's say. So the center value will be unique, as you know, and then you will have samples like this to the left and right of it. Let me just extend this a little. Okay. And 9. So let us say this is an example of the impulse response of the system that we have. The first sample is at 0. The last sample is m minus 1. So the center point exactly here is m minus 1 by 2, where we have the center sample m minus 1 by 2. Okay. So now, like we did in the case for m being even, we derived an expression for h of omega, right? So the same thing, let's do it here now. So first we'll write down the Z transform of the impulse response, and then we are going to simplify it to get the frequency response. Okay, so what is h of z? H of z is summation n 0 to m minus 1, because there are samples only from 0 to m minus 1 in h of n. So that is how the limits on the summation are going to change. H of n z to the power minus n. Okay. So now what we'll do is we will split the summation. So in the m even case, we split the summation into two portions, right? The first half portion and the second half portion. Here exactly you will not have first half and second half because m is odd here, right? So we have this sample, the center sample, that is unique, whereas these samples on the left and these samples on the right, okay, they are symmetric and they are equal. So we'll split the summation n from 0 to m minus 1 into the first half consisting of these samples, okay, then a single term with the center sample, and the second summation with these remaining samples that we have. Okay, is that fine? So the first summation starts at n is equal to 0. So what is this value? So how do you get this value? M minus 1 by 2. Okay, one value less than this, right? So minus 1. M minus 1 by 2 minus 1. So what is that? M minus 3 by 2. So this is going to become m minus 3 by 2, this sample, m minus 3 by 2. Fine. So this limits will be from n0 to m minus 3 by 2. The first portion of the samples that we are taking. Then h of n is going to be as it is, z bar minus n plus this value, that is the center value that we have. So we are going to substitute n equals m minus 1 by 2 to just uniquely write the center value. So what is that? H of m minus 1 by 2, z bar minus of m minus 1 by 2. That is the center value. Okay. Plus the next summation, the values, that is the remaining values we'll have to write. So summation n from, so this sample is what I have to write now. So how do you obtain the index of this sample? M minus 1 by 2, because this is the reference for us, m minus 1 by 2 plus 1, isn't it? Because it is one sample later. So m minus 1 by 2 plus 1. So what will be that value? M plus 1 whole divided by 2, isn't it? So this sample will be m plus 1 whole divided by 2. So that is the sample. So here the limits will be from m plus 1 by 2 to m minus 1. H of n z bar minus n. H of n z bar minus n. Okay, and also you can see that since the values are symmetric, your frequency response that we are writing just require only half the number of samples. Okay, only with half the number of samples we can write the frequency response. That is because of the symmetry property of the impulse response, and that's exactly what we are trying to do here. Okay, now what do we do in the second summation? Like we did in the previous case, in the second summation, let us substitute here n equals m minus 1 minus small m. We'll make a substitution n equals m minus 1 minus small m in the second summation or the third term that we are talking about. So the lower limit, when you put n equals m plus 1 by 2, right? What will be the value of m? M is m minus 1 minus of m plus 1 by 2. M plus 1 by 2. So what will that be simplified to? You are going to get m minus 3 by 2. M minus 3 by 2. M minus m by 2, you're going to get m by 2. Then minus 1 minus 1 by 2 is minus 3 by 2. So combining that, we can write small m as m minus 3 by 2. Similarly, the upper limit, when you put n equals m minus 1, small m becomes 0. Small m becomes 0. So the limits are going to change, and let's make the substitution in the third term. So that will be, so the first term, we just keep it as it is, n0 to m minus 3 by 2, h of n z bar minus n plus h of m minus 1 by 2 z bar minus of m minus 1 by 2 plus summation, okay, m from m minus 3 by 2 to 2 to 0. Also write that as 0 to m minus 3 by 2, because it is a summation. We have just interchanged the limits. Then h of n. So in place of n, you have m minus 1 minus m. Okay. Z bar minus of m minus 1 minus m. 1 minus m. Making the substitution. Okay. Now, obviously, I would want to combine the first and the last summation. I can do that, right? So instead of having the variable m here, like we always do, we can have the variable n, because since it's just a variable, it can be changed to n. It does not matter. So that's what I have done. So now we know that the impulse response is symmetric. So what does it satisfy? H of n is h of m minus 1 minus n. H of m minus 1 minus n. So what is this term? This term can be replaced with h of n, isn't it? We can replace h of m minus 1 minus n with h of n because the impulse response is symmetric. Now we can combine the first and the last summation because the limits are the same, right? The limits are the same and we have h of n a common term. We have h of n as a common term. So we can combine the first and the last summation. So the center term, I'll just write it here like this, plus summation n0 to m minus 3 by 2, h of n is common. Z bar minus n plus z bar minus of m minus 1 minus n. So that is your expression for h of z that we have obtained when h of n is symmetric and it is odd. Okay. So now we can obtain the frequency response of the system by substituting for z. So what you're going to substitute for z? If you put z equals e power j omega, you're going to get the frequency response of the system or the DTFT. So let's do that. So h of e power j omega is h of m minus 1 by 2 e power j omega. You have minus of m minus 1 by 2 plus summation n0 to m minus 3 by 2 h of n e power minus j omega n plus e power minus j omega m minus 1 minus n. Okay, by substituting for z. Substituting for z. The simplification goes in a very similar fashion, like how we derived in the previous case for m being even. Only thing is the limits and certain terms are going to be different. So now we'll have to simplify this term here, the exponential term, so that we can write that in terms of cos, and also you can write it in the polar form, that is r e to the power j omega. So already you have this term here. See, you have already have this, the first term in the form of r e to the power j omega, but the second term needs to be written in that form. So what shall we do for that? We are going to, yeah, the first term will be as it is, so which I am going to write here, plus in the second term, let us take e power minus j omega into m minus 1 by 2 as a common value. Okay, so the first term, how does it simplify to? The first term will be e power minus j omega. Okay, I'm going to keep that, and n here. then minus of m minus 1 by 2 I'm going to write here. So if I do that and if you multiply these two terms again, you are going to get back this first term, isn't it? Because you have e power plus j omega into m minus 1 by 2 in this term here. You're going to get back that plus in the second term e power minus j omega, or rather it will become plus here now, because in that m minus 1, let's take out m minus 1 by 2. So n minus of m minus 1 by 2. E power plus j omega. So you can just multiply it back and check if you're getting the previous term, which you're going to get. E power j omega n you will get, and m minus 1 by 2, m minus 1 by 2 with a negative sign, which will become minus of m minus 1. So you're going to get back the previous term. But now this exponential term and this exponential term together can give us the cost term. Right? So the first term h of m minus 1 by 2 e power minus j omega into m minus 1 by 2. The first term as it is. Plus, so this term can be written outside the summation as a common factor. Why? Because it has no n term in that. There is no n term there. So we can write it outside the summation. Outside the summation. So what remains will be summation n 0 to m minus 3 by 2 h of n. So in the bracket, the term amounts to cos, right? So 2 cos of n minus of m minus 1 by 2. N minus of m minus 1 by 2. Okay. So now the entire expression for h of e power j omega, we have to write it in r e power j theta form. R e to the power j theta form. So this term that we have is common, right? Which can be written outside. So what is remaining? H of m minus 1 by 2 plus summation n0 to m minus 3 by 2 2 h of n cos n minus of m minus 1 by 2. Okay, so this entire term multiplied with e to the power minus j omega into m minus 1 by 2. Okay, so have we written h of e power j omega as a polar form, in the polar form, or e to the power j theta form? So what is your r?
Excuse me, ma'am. Ma'am, we should get omega inside cos, no, ma'am. Omega into n minus m minus 1 by 2.
I missed that out. Yeah. There is a omega. Yeah, there is a omega here. Yeah. So one more bracket anyway. Okay. So what is your magnitude term, or we write that as hr of omega is this first term, h of m minus 1 by 2 plus summation n0 to m minus 3 by 2 2 h of n cos of omega into n minus of m minus 1 by 2. That is your magnitude part, and the phase phi of omega is minus omega into m minus 1 by 2. e to the power j theta. So theta is minus omega m minus 1 by 2. So this is provided your HR of omega is positive. So like we saw yesterday, if HR of omega is a negative, then you will have a plus pi in the phase. The phase shifts by pi units. So minus omega m minus 1 by 2 plus pi. So whether HR of omega is positive or negative, if you look at the expression for the phase response, it is a linear phase. The equation is a linear equation, right? So the phase response is a linear phase response. It's a straight line. The slope is minus of m minus 1 by 2. Negative slope it has, but it's a linear phase. A very important characteristic of FIR filters. Okay, so what we have done now is we have derived the expression for the frequency response of the filter, FIR filter, when H of n is symmetric and for m even and odd case. So like I told you, derivations are important in DSP. They could ask you any of the derivations for that matter. Okay, the filter design procedures, all of them are important. So theory part, you can expect questions here. And also, like I told you, in the filter design problems, the specifications, the filter specifications will be given to you. You will have to derive H of n, obtain H of n. So the procedure we are going to follow for that, we'll go to it in the next topic. So you're going to get the H of n values, the filter coefficient values, which you have to then substitute in these equations, okay, to obtain the frequency response. So that's a complete filter design problem, obtaining the filter coefficients, that is H of n values, and writing down the frequency response of the filter. Okay, so in the same fashion, if the impulse response of the filter is anti-symmetric, even then the linear phase response is going to be satisfied. Okay, in the same manner, like we derived for n even and n odd, the order, capital M being even and odd, you can derive the frequency response equations when H of n is anti-symmetric. Okay, so I'll just tell you what are the conditions for that, and I want all of you all to do this by yourselves because it's very much based on the same lines. Okay, so an anti-symmetric H of n, anti-symmetric condition of the impulse response. So when do we say it is anti-symmetric? If H of n is minus H of m minus 1 minus n. It is anti-symmetric about the midpoint. So what is the midpoint? It is at m minus 1 by 2. M minus 1 by 2. So you know that for an odd sequence or an anti-symmetric sequence, this is always 0. Okay, it used to be the origin for us for the signal that we discussed. The origin point for an odd signal is 0. The value is 0 there because 0 equals minus 0 condition cannot be satisfied. Whereas the samples which are about the center point will be anti-symmetric or negative amplitudes of each other, right? So the center value H of m minus 1 by 2 will always be 0 for an anti-symmetric signal or an odd signal. So keeping that in mind, you can write down like how we wrote previously, draw the H of n for an anti-symmetric, m even and m odd, right? And perform the derivation in the same fashion. So I'll give you the expressions for these. You may have to remember it because whenever you're doing the filter design, if the H of n that we obtain is anti-symmetric, then you'll have to use this expression for the frequency response of the filter. Okay. So h of omega, if you derive for this, you're going to obtain as hr of omega e power j minus omega m minus 1 by 2 plus pi by 2, where hr of omega will be 2 summation n0 to m minus 3 by 2 h of n sine omega into m minus 1 by 2 minus n. So you can expect a sign here, right? Why? Because the signal is anti-symmetric, negative of each other. The samples that are there in the first summation, if it is positive, the second summation terms are going to be negative. Okay, so that's why we get a sign term here. So this is expression when m is odd. This is for m is odd. Then for m even, hr of omega will be 2 summation n0 to m by 2 minus 1 h of n sine of omega into m minus 1 by 2 minus n. This is when m is even. When m is even. So just look at the phase response. Minus omega into m minus 1 by 2 plus pi by 2. Again, it's a linear equation, right? It's a linear equation. So that linear phase characteristic will always be there for a FIR filter. So the phase response is minus omega into m minus 1 by 2 plus pi. This is when hr of omega is positive. So obviously when hr of omega is negative, there is a plus pi. So this is pi by 2 that you're going to obtain. So this expression you're going to obtain when you derive the equation actually. Okay. So if it is negative, there will be a plus pi. So that becomes 3 pi by 2. Right? When hr of omega is negative, plus 3 pi by 2. 3 pi by 2. That will be the phase response for an anti-symmetric filter. Anti-symmetric filter. So even in the lab, you're going to actually design an FIR filter and plot its filter coefficients and the frequency response. So then you can observe this characteristic of the FIR filter, that it is symmetric about the midpoint. Okay. So with that, we have derived the frequency response. So we talked about linear, phase, symmetric and anti-symmetric filter coefficients or the impulse response of the filter. Okay. So again, depending on the kind of application, we either choose an anti-symmetric filter or a symmetric filter. That depends on what kind of application you're using the filter for. Now coming to the problem of designing a filter, okay, or filter design. What is the procedure that you're going to adopt to design the filter, or that is to obtain the filter coefficients h of n. So when I say filter coefficients, it's nothing but the h of n, the impulse response that I'm talking about. Okay. So in order to derive the filter coefficients, there are several methods available actually, but what you're going to be learning here is called as the window technique of designing the FIR filter. So that's one major filter design procedure that we are going to understand here. And also we have one more technique which is called as the frequency domain sampling technique, frequency sampling technique. It's very similar to what frequency domain sampling. Again, if you go back, we had discussed this in the derivation of DFT, right? So something similar to that we are going to be doing. But this window technique of designing an FIR filter is quite popular, and it covers majority of your syllabus as well. So what is this filter design technique using the windows? So design of linear phase FIR filter using window technique. Using the window technique. So here, if I have to tell you the gist of this method of designing the FIR filter, the desired frequency response of the filter will be given to you. Okay. When I say frequency response, we are talking about the frequency domain, the characteristics of the filter in the frequency domain. Now let us say it's a low pass filter that you want to design. Okay, so what is the characteristic of a low pass filter? Ideally speaking, this is how we expect it to be, to have a very flat pass band. So you call this as the pass band, a very flat stop band, and a very sharp transition band. So this is an ideal filter. This is an ideal filter which we cannot reach practically actually. So practically speaking, how is the response of your low pass filter going to be? You expect a smooth transition like this. Now for an FIR filter, the pass band and the stop band will not be flat, or it will not be a smooth one. Instead, the ripples in the pass band and the stop band. Okay, so we are going to have some ripples in the pass band, and then you'll have a smooth transition band, and again ripples in the stop band. Okay, so this happens for an FIR filter. One main because of the kind of the window technique that we are using. Because of that also the ripples are going to be present. Okay, and it's a practical filter. We can make it a little closer to the ideal, but the ideal case is not possible to achieve. Okay. So what will be given to you is this frequency response. So when we say the filter specifications, what is it that we are talking about? Okay, so when we say filter specifications, so what all specifications can you expect in a filter? You expect some cutoff frequency, right? Now, if this is your frequency response, then this is the end of your pass band, right? So what is the frequency where the pass band ends? That is represented as omega p, or the pass band edge frequency, right? Omega p is called the pass band edge frequency, where the pass band is going to end. And then this is your transition band, correct? Shall I just write it here? This is transition band, this is your pass band, and this is the stop band for a low pass filter. Okay, then where does your stop band starting? That is represented as omega s. So what is omega s? Stop band edge frequency. Stop band edge frequency. So this filter characteristics is with respect to omega that we are talking about. So this is your HD of omega. That D indicates that it's the desired frequency response. What is it that is desired for you to obtain the frequency response? Okay, HD. HD of omega, D indicates the desired frequency response. If I didn't spoil that. HD of omega. So omega P, omega S will be given to you, and then the ripples in the pass band and the stop band will be specified, the magnitude of the ripples. So if you look at this range, okay, so this one plus delta 1 we'll call, and this has 1 minus delta 1. The ripples in the pass band are varying between the amplitudes 1 plus delta 1 to 1 minus delta 1. This is a magnitude that we are talking about. we will also draw the dB scale. What is a dB scale? If you take 20 log of the magnitude is the decibel scale that we are talking about. Okay, so that also we are going to draw in the IAR filter. Here it is the magnitude response. So this value here is 0, the origin. Then the ripples in the stop band is represented as delta 2. The ripples in the stop band is represented as delta 2. So these are called as the filter specifications. So they are going to give you omega p, omega s, delta 1 and delta 2. So if these 4 parameters are given to you and they say that it's a low pass filter, you can easily draw this frequency response, isn't it? You know which are the pass band edge frequencies and what is the ripple that you're going to expect in the pass band and the stop band. So this frequency response is quite obvious because for a low pass filter there is no other frequency response, right? So you can draw this given frequency response. So these 4 values that we are talking about, omega p, omega s, delta 1 and delta 2, these are called as the filter specifications. These are called as the filter specifications. So this will be given to you in the problem. This will be given to you in the problem. Okay. So what is HD of omega then? That is given to you, right? So what is the design procedure or this window technique? So like I told you briefly, if I have to tell you what that is, HD of omega is going to be given to you. You will find the impulse response to this HD of n. How? Using the inverse DTFT formula. Because HD of omega is nothing but the DTFT of the signal. So when HD of omega is given to you, using the inverse DTFT formula, you can find HD of n. Okay, so as you can see, no concepts from signals can be forgotten here. Everything we are going to be using it. And again, further in many of your communication subjects also you'll be using those concepts. Okay, so using inverse DTFT, we find HD of n. Okay, so this HD of n, what we obtain happens to be an infinite duration sequence. The HD of n that we obtain happens to be an infinite duration sequence. But what is the filter that we are designing? It is a finite impulse response filter, an FIR filter, which has finite number of samples in it. How many samples? M samples exactly, from 0 to m minus 1. Okay. So what we do is this HD of n, which is an infinite impulse response that we have obtained by taking the inverse DTFT, we'll multiply this with the window function. Okay, that happens, right? If you have some signal, if you have some signal like this, which is going on varying from plus infinity to infinity, with a window function which is defined only from some problem with my board. Yeah, so this is defined only from 0 to m minus 1. 0 to m minus 1. So now what happens if you multiply this infinite duration sequence with a finite duration sequence? You're going to just get the samples from 0 to m minus 1. So this function that we are multiplying is called as the window function. And to be very specific, it's a rectangular window. Okay, this is a rectangular window. Finite duration sequence with a rectangular window. So then what we obtain is a finite duration sequence, and that is the desired h of n for us, the filter coefficients or the filter coefficients of the FIR filter that we have obtained. Okay, so since you are multiplying the HD of n with a window function, this technique is called as the window technique. Okay, this technique is called as the window technique. So it's not only the rectangular window that we have other kinds of windows also. So why we go in for the other kind of windows, that we will see later. Okay, why that happens to be. So is the overall concept clear to you? HD of omega will be given. How do you write the expression for HD of omega? We'll see. HD of omega will be given to you. Using the inverse DTFT, you have to find HD of n. But you know from the DTFT concept that HD of n will be an infinite duration sequence. But we are interested in designing a finite duration impulse or a filter which has a finite impulse response. So what we do is we multiply this with a rectangular window of size m or defined from 0 to m minus 1. So we pick out only those samples in the interval 0 to m minus 1. And that will be your desired FIR filter coefficients, h of n. Okay. So you could ask, won't there be any problems if you just pick out these samples and leave out the remaining? Yes, there are problems, and these ripples which we obtain in the passband and the stop band are partially because of this reason, because we are truncating the values. That HD of n, what we had, the values which was, it could be gradually going down to 0 at some point. Okay, but we are truncating them suddenly to 0 and m minus 1. So this causes ripples in the passband and the stop band frequency response. So this which we have written, it causes these ripples in the passband and the stop band. This the phenomenon that happens because of truncating the values is called as the Gibbs phenomenon. Yes, it is a disadvantage, one of the disadvantages, but then it's one way of designing the FIR filter. Okay. So now what we have to do is we'll have to write down all the equations clearly. What is HD of omega? How do you write HD of n? Okay. And also some of the discussions which we do it in the frequency domain, time domain. So we keep on shifting from time domain to frequency domain. So that you should now observe actually. Okay, so the shifting that is happening. Once I say frequency response, I'm talking about the frequency domain. Once I say impulse response, I'm talking about the signal in the time domain. Okay, the shifting that we are happening, you should be able to visualize these things now. Okay. So now we'll have to write the equations and do some more analysis. So let's just do that. I hope this is clear, whatever I told you till now. So now let's derive the equations for the filter design procedure. And then what we'll do is we'll write down the filter design procedure stepwise, what you have to do from the beginning till the end. So finally, when you are working out a problem, these the filter design procedure will be sufficient for you to solve the problem. But concept wise, when you're trying to understand something, these derivations are important. Okay. Yeah. So like I told you, HD of omega, the desired frequency response will be given to you. The desired frequency response. Using the inverse DTFT formula, find HD of n. Find HD of n. So what is that formula? 1 by 2 pi integral minus pi to pi HD of omega e power j omega n d omega. E power j omega n d omega. That is the expression for HD of n, that is the inverse DTFT formula. Okay, so this HD of n that you obtain is of infinite duration. This is of infinite duration. Let us multiply n. We will multiply HD of n with a window function. With the window function. The simplest of this is the rectangular window, right? So what is the window function? Rectangular window that we are using. Simple. It has an amplitude of 1 in the interval 0 to m minus 1 and 0 otherwise. A very simple window that we have considered is W of n. So if you multiply HD of n, multiply HD of n that you obtained with W of n. So now the samples will come down to just samples from 0 to m minus 1. So that became our FIR filter H of n. So H of n is the impulse response of the FIR filter that we are interested in designing. So H of n will be what? HD of n in the interval 0 to m minus 1, and it is 0 otherwise. So an infinite duration impulse response, we have just reduced it to a finite number of samples. Okay, so overall to say that is your the overall procedure for filter design. But then we'll have to do some more analysis and relate it to the frequency response that we expression that we derived. Okay, what is the slope that you have to take and how do you get the m value, the order of the filter, how do you decide? Okay, all these concepts will be there for the filter design, and formally we have to write the expression for HD of omega, how it is going to be, because HD of omega we just cannot take anything because this is a linear phase response filter. So accordingly we'll have to write down what is HD of omega and then derive HD of n and write the equations properly. Okay. Before that, let us perform some of the analysis in the frequency domain, and also we have to see the different kind of windows that are available to us. Okay, it's not only the rectangular window that we can use. There are other kinds of windows as well. So which is going to reduce the ripples that is obtained, that happens in the passband and the stop band because of multiplying with the window function. It's going to reduce to some extent, not fully make it a flat passband and a stop band. Okay. Whereas if you talk about an IAR filter, the IAR filter has a flat passband and a stop band. Okay. So again, it depends on the kind of filter that you're designing. Each of them is different. Okay. So you have different kinds of filters. Based on the application that you want to use it, you can select those filters that you want. Okay. So now to do the analysis in the frequency domain, what is it that we have to observe, or why is it needed? Okay, yes. So now if you look at this expression of HD of n into W of n, if you write the frequency response characteristic of this, or write the frequency domain representation of this, right? So that will become, that is for this expression, I'm writing the DTFT. The DTFT H of omega will be equal to HD of omega. This is multiplication here, which becomes convolution in the frequency domain into capital W of omega. Into capital W of omega. This will also give you the justification why those ripples actually arise in the frequency response, H of omega. So, of omega we know is like something like your low pass filter response. Okay, let's say it is ideal only. What we start off with an ideal. Okay, so HD of omega is an ideal low pass filter frequency response. How about your W of omega? How is your W of omega going to be? So what is W of n? A rectangular function. Correct? A W of n is a rectangular function. So what do you expect W of omega to be? It has to be a sinc function, isn't it? A rectangular function in one domain will be a sinc in the other domain. So if you derive the expression for W of omega, it has to be a sinc function. So let's just derive that quickly. So W of omega, DTFT formula, W of omega will be summation n0 to m minus 1 W of n e power minus j omega n. So what is W of n? It is 1. n0 to m minus 1, 1 e power minus j omega. Summation, what will this be? 1 minus e power minus j omega whole to the power n, right? What you have. So that will be capital M here by 1 minus e power minus j omega. So with this you cannot make out whether it's a sinc function or not. So what we have to do? We have to simplify. So let us simplify that. We'll take e power minus j omega m by 2 as a common factor in the numerator. So this term will be e to the power plus j omega m by 2, correct? Minus e power minus omega m by 2. That is the term in the numerator. Then denominator. Denominator, let's take e power minus j omega by 2. So this will be e power plus j omega by 2 minus e power minus j omega by 2. Okay. So let's now combine the numerator and denominator exponentials. So with that, it's e power minus j omega m minus 1 by 2. Correct? M minus 1 by 2. Minus omega we've written common outside. What is this? 2j sine omega m by 2. Denominator is 2j sine omega by 2. Omega by 2. So these two terms get cancelled. What is a sine by sine term? It is a periodic repetition of sinc. Why? Because DTFT is periodic, right? It's a periodic repetition of the sinc function, the expression that we have obtained. So this is your magnitude response. Sine by sine is the magnitude response. And just have a look at the phase response. See the phase response. Isn't it linear? Yes, it is linear. So all the window functions that we select, along with the frequency response to the filter that you are designing, along with that being linear, even the window function also is a linear phase, because this should not distort the phase response of the filter that we are designing. So the window also has a phase. So this is like now getting back to the equation that we have here. What is it that we are now checking? You are observing this expression. HD of omega getting multiplied with the window function. What is it that is happening in the frequency domain? So see here, this is your, let us say, an ideal low pass filter response which I want, HD of omega, that is given to you, HD of omega. This you are convolving with the sinc function. This you are convolving with the sinc function. What is this? W of omega, the frequency response of the window function. So when you convolve these two functions, what do you expect? This sinc function, your convolution, how does it happen? You're going to shift this this function to the left, and then you're going to keep on shifting it right and multiplying with this function, right? So can you expect something like this to happen? So the straight response which was there, ideally, since you're convolving with this sinc function, okay, you can expect ripples in the passband. Likewise, some gradual transition, and then ripples in the stop band. Ripples in the stop band. So like I told you, right, since you're multiplying the infinite duration sequence HD of n in the time domain with the window function, You cannot make out that what is happening actually in the time domain. You'll have to look at it in the frequency domain to see what exactly is happening. So if you look at what is happening in the frequency domain, there is a convolution that is going on, okay, a rectangular function with a sinc function. So obviously you can expect a waveform something like this. So this is what you actually get, the frequency response that you are going to actually obtain than the ideal that you started off with. Okay, so the ripples in the pass band and the stop band and the smooth transition can be explained to this process that is happening in the frequency domain. So that is the reason why we keep on switching between domains. There are certain things which can be observed in the time domain but cannot be observed in the frequency domain, and the vice versa is true. So always the analysis needs to be done in both the places. Okay, both the places, so that you know exactly what is the effect that is happening. Okay, so is that clear for everyone? So now let us see the design procedure for an FIR filter. For an FIR filter using the window technique. Using the window technique. We'll write the equations one after the other and also see whether we can use just one window or there are other kinds of windows also which are available to us. But how do you decide which window to use? Okay, so all those points we are going to be looking now. So this is the design procedure that you have to follow whenever a problem is given to you. Okay. So now we'll have to start off with an ideal filter response, frequency response. So we will derive the design procedure for a low pass filter, but you can also design a high pass filter, a band pass filter, or a band stop filter. So these are the four kinds of filters, right, that we have: low pass filter, high pass, band pass, and band stop. So any of these four filters can be designed. Only difference is the HD of omega that we are going to write in the beginning. Okay, what is HD of omega? HD of omega is the desired frequency response of the filter. Desired frequency response. And this is the ideal response that we start off with. Ideal response that we start off with. So suppose a high pass filter is given to you to be designed, then this HD of omega, accordingly you'll have to write it down. So first let's understand for a low pass filter, and then I'll tell you how do we do it for a high pass or a band pass. It's very easy, just an extension of this, what you have to do. Okay, so we have to first write down HD of omega for a low pass filter, and you should keep in mind that this should have a linear phase. It should have a linear phase. So let us assume a linear phase of slope minus alpha. So why have I taken a negative slope? Because we have seen in the derivations before, that is, whenever you take a symmetric impulse response, the frequency response what we got, the phase response especially, which we have written, the four equations which I have given you before, has a negative slope. Okay, so that is why I have assumed a value of minus alpha here. Okay, so we are considering an ideal frequency response of a low pass filter with a linear phase of slope minus alpha. This is HD of omega. So what is the equation for this HD of omega? Yeah, and one more, the cutoff frequency. The cutoff frequency is omega c. Let's denote it as omega c. So all these are digital specifications that we are talking about. Okay. So if I write the frequency response, how does it look like for a low pass filter? Omega. So it's ideal. Therefore, until omega c, it will pass all the frequencies, and up till here, it is going to stop. Why have I written till pi? And of course, you know how the frequency response looks like. The magnitude response will be symmetric. This is basically the DTFT, that we are talking about. You always have a symmetric magnitude response, and it is defined from minus pi to pi, and this is periodic, right? It has a period of 2 pi, and this repeats. So we don't have to write the periodic version of it. We just take one period of the response. Okay, so this is basically the DTFT function that we were talking about. So this is a low pass filter, and we denote this as HD of omega, HD of omega. And how does your phase response looks like? Talk about a phase response for an FIR filter, whereas for an IAR filter we don't worry so much, because anyway for an IAR filter the phase could change. It may be linear, it may not be linear. Okay, so we don't worry so much about the phase for an IAR filter. So this has a linear phase response with a negative slope. So this is pi for the entire duration from plus pi to minus pi. Okay, so it has a negative slope of minus alpha. Negative slope of minus alpha. So this is your phi of omega. So how do we write the equation for this frequency response? So why we have to write the equation? Because we need to find HD of n next using the inverse DTFT. So how do we write the equation for this low pass filter? Characteristic is so HD of omega can be written as 1 e to the power minus j omega alpha in the interval of omega, magnitude I am writing, less than omega c. So for omega less than omega c and omega greater than minus omega c. This is minus omega c. So between minus omega c and plus omega c, the frequency response has a magnitude of 1 and a phase response with a slope of minus alpha. That is all. Whatever we told in statements here, we have written in the form of an equation for HD of omega. Okay, so that is the equation. And why this is 1? Because this phase response has a value of 1. I mean, the magnitude response has a value of 1 here. It passes all the frequency components between minus omega c and plus omega c, or between 0 to omega c, because it is a low pass filter. Because it is a low pass filter, and we will cut off all the frequency components beyond omega c. Beyond omega c. So that's a low pass filter, and it is 0 for magnitude of omega greater than omega c and less than pi. Less than pi. So that is in the interval omega c to pi, and this side minus pi to minus omega c. The value is 0. Okay. So this equation of HD of omega will not be given to you in the problem. They will just tell you design a low pass FIR low pass filter. So you will have to start with this equation of HD of omega. So you should know that a linear phase low pass FIR filter, the desired frequency response, the ideal case is what we want to do. So you will have to start off by writing this equation. Is that clear? Okay. Now, using the inverse DTFT formula, let us find out what is HD of n. Let's find out what is HD of n. So we know with the inverse DTFT formula that HD of n is given as HD of n is 1 by 2 pi integral minus pi to pi HD of omega e power j omega n d omega. Okay, so let's integrate that, and before that let's substitute the value of HD of omega. So what is HD of omega? It is non-zero in the interval minus omega c to plus omega c, correct? And the value is e to the power minus j omega alpha. Then we have e power j omega n d omega. So let's integrate this. Let's combine both the exponentials and we shall integrate. Okay, so what do we get? If you integrate that, 1 by 2 pi. So I'll combine both the exponentials and integrate at the same time. Can I do that? So e power j omega into n minus alpha. I'm going to write the exponential like that. So if you integrate this, it's divided by, the integration is with respect to omega. So divided by j into n minus alpha between the limits minus omega c to plus omega c. Between the limits minus omega c to plus omega c. Let us substitute the limits. 1 by 2 pi j into n minus alpha. I'll just write it down this side as a common factor. So j omega c n minus alpha minus e to the power minus j omega c into n minus alpha is what we have substituted. Okay, so obviously your numerator can be written in terms of sign. So what will that value be? 2j sine of omega c into n minus alpha divided by 2 pi j into n minus alpha. So 2j gets cancelled. You are left with sine omega c into n minus alpha divided by pi into n minus alpha. Pi into n minus alpha. Okay, so that is hd of n. hd of n. So should we stop at this point? The value of hd of n. So can we put all values of n in this equation? No, right? If you put n is equal to alpha, what happens? It becomes a 0 by 0 form. If you put n equals alpha, it becomes sine 0 by 0, which is an indefinite form. So definitely you cannot put the value n is equal to alpha in this case. So this equation is valid for all values of n except n equals alpha. Except n is equal to alpha. Okay. So what is the value at n equals alpha? That also we should find out. So what's the value at n is equal to alpha? How do you find out? Go to this equation. Go to this equation and you can substitute in this equation n is equal to alpha. So what happens if I put n equals alpha? E power minus j omega alpha into e power plus j omega alpha. That will be e power 0, which is a 1. Therefore, when n is equal to alpha, hd of n will be 1 by 2 pi integral minus omega c to plus omega c minus omega c to plus omega c 1 into d omega. 1 into d omega. So again, let's integrate and substitute the limits. So omega between the interval minus omega c to plus omega c. So that's going to be 2 omega c divided by 2 pi. 2 gets cancelled. You get omega c by pi. You're going to get omega c by pi. So the value at n equals alpha is omega c by pi. Same thing, it's very similar to a sinc function, isn't it? Similar to a sinc function. So this sinc function, what you can expect at n equals alpha, it will have a maximum, right? At n equals alpha, it has a maximum of omega c by pi and the value goes on decreasing. You know how a sinc function looks like. It goes on decreasing and there are ripples on the left side and on the right side. But it's a symmetric function. Correct? It is a symmetric function. About the point n is equal to alpha. About the point n equals alpha. I am talking about hd of n. Okay. So now what is the next step in your design procedure? So you know that HD of n is an infinite duration sequence. HD of n is of infinite duration. This we know from the property of the Fourier transforms. So what do? We multiply HD of n with the window function. So the window is defined. Let me write it here. The window, the rectangular window, is defined as having a value of 1 between the interval 0 to m minus 1 and 0 otherwise. So there are m samples defined from 0 to m minus 1 in the window function. So h of n is hd of n into w of n. So when multiplying these two, what happens? Your h of n just will have only m samples in it, a finite duration impulse response. So those will be the filter coefficients of the FIR filter, the h of n value. So let's write the equation for this. What is hd of n? Sine of omega c into n minus alpha divided into n minus alpha into what is w of n value? It will be 1. Okay, this is in the interval 0 to m minus 1. 0 to m minus 1 because you are multiplying there. And m is called the order of the filter. M is called as the order of the filter. The number of samples that are there in h of n. And it is, what is the value? So here n is not equal to alpha. N should not be equal to alpha. But when n is equal to alpha, what is the value? Omega c by pi. Omega c by pi. So that is the equation of h of n. So if you have to find h of n, right, omega c will be given to you in the problem. The cutoff frequency of the filter will be specified in the problem. That is omega c. So what else we have to know in this? What else are the values that we have to know? Obviously it is alpha. You should know what is the value of alpha and you should know what is m. Isn't it? So these two values needs to be found out. So what is the value for alpha and m that we have to consider? Now your window function w of n, it's a symmetric, correct? Function is symmetric about which point? About the center point. About the center point, that is m minus 1 by 2, correct? So the window function is symmetric about the point n equals m minus 1 by 2, exactly the center. Because it's a rectangular function, we can say it is symmetric about the center. Then hd of n, that is this sinc function which we have got. This is symmetric about which point? I told you n equals alpha, it is maximum, correct? N equals alpha, it's maximum, and then it gradually tapers down. Okay, how does your sinc function look like? Like this. If this is alpha, you will have a maximum value there, discrete, right? So, and it will go on decreasing like this. The sinc function is going to go in this fashion. That is how your sinc function is. So where is the center or rather what is the point about which it is symmetric? That is n is equal to alpha, it is symmetric. At n equals alpha, it has a maximum value and it is symmetric about this point. Okay. So why I am telling you this is your h of n that we design, the h of n that we are going to design, the FIR filter that we design should be a symmetric filter. Should be a symmetric or antisymmetric. When I say symmetric, it also implies that antisymmetric also could be a possibility. But here we have got a symmetric function, that is the sinc function. So h of n also should be symmetric. Why should it be symmetric? So that a linear phase response is maintained or obtained. A linear phase response is obtained. So we have to make sure that h of n is symmetric. So how do you do that? Obviously, if you take the value of alpha to be m minus 1 by 2, if you set this value of alpha, then automatically h of n becomes a symmetric function. See, hd of n, what you have obtained is an infinite duration sequence. It goes on either side of n equals alpha. Why n equals alpha is the maximum value? Because that is omega c by pi. You can substitute the values and check if you want. Okay, omega c by pi in this case will be the maximum. That is the center lobe, the center value. And beyond that, the value goes on decreasing because it is a sinc function. It has to decrease in that fashion. So that means to say n equals alpha is the point about which hd of n is symmetric. So if you are multiplying this with a window function, let me write the window function here. If you are multiplying this with a window function like this, from 0 to m minus 1, if this is symmetric about m minus 1 by 2, right? If you set the value of alpha to something else, what happens? You may not get a symmetric function. That is, h of n could not result in a symmetric function. But if you set the value of alpha to be m minus 1 by 2, then when you multiply this hd of n into w of n, your h of n also will be symmetric in nature. It will also be symmetric in nature. Okay, so we got the condition for alpha. How do you find out alpha? Using m. The next question is, how do you find out m? The order of the filter. How do you decide what should be the order of the filter? Okay. Now this depends on the stop band attenuation that is given to you. For different filters it is different. Okay. For an FIR filter, how do you decide the value of m is depending on the stop band attenuation of the filter that will be given to you. Okay. The stop band attenuation of the filter that will be specified in the problem. I told you, right? There are 4 filter specifications that will be given to you. Pass band edge, stop band edge frequency. In case of IAR filter, they give you these 2 frequencies. But for an FIR filter, it is just one cutoff frequency. That is omega c. So how do we calculate omega c using pass band? That I will tell you. So omega p and omega s, right? And delta p, delta s will be given to you. Delta p, delta s are the ripple in the pass band and stop band. These are magnitudes. These are magnitudes. In the decibel range also it can be given in terms of decibels. So based on the stop band attenuation that is given to you, okay, you have to select the window function. So far we have just talked about rectangular window, but rectangular window is not the only option. We have other windows also like Hamming window, Hanning window, Bartlett window, okay, and there are various others also, Blackman window, Kaiser window, all that is there. But in the syllabus, it's the 4 windows are specified: Bartlett, Hamming, Hanning, and rectangular. So how do you select which window to use? It depends on the stop band attenuation. So looking at the stop band attenuation, select the kind of window function that you are going to be using. Okay. For each window function, there is a different m that you can select. So I'll just give you a table here. Okay, where, that is the stop band attenuation and the value of m that can be selected using this window. So this table needs to be referred and you have to choose the window according to that. Okay. So let us just list the windows. So the name of the window, what is the window, and each window will give you a different transition width. Okay, why the transition width happens? Because of that convolution that is happening in the frequency domain. The window function getting convolved with the ideal frequency response. That is why the transition is not sharp, it becomes smooth, because this window function in frequency domain is a sinc function. So different windows will give a different smoothing effect. Therefore, the transition width given by the different windows will be different. What is transition width? Transition width. Okay, if I have to draw a low pass response here, so this is how it's going to be, right? This will be omega p, pass band edge frequency. This is omega s, stop band edge frequency. So this portion is the transition width delta omega. So what is that? Omega s minus omega p. Delta omega, the transition width, is nothing but omega s minus omega p. So that will be different for different windows. Then stop band attenuation. Stop band attenuation. Yeah, the pass band attenuation is not seen in this case. Only depending on the stop band attenuation, we select the window. Okay, so first one is a rectangular window. Rectangular window. The rectangular window gives a transition width of 4 pi by m. What is m? Order of the filter. And it gives an attenuation of minus 21 decibels. So stop band attenuation is in decibels. So check the stop band attenuation of the given filter design problem. Based on that, select the window. Once you select the window, you will get the transition width. You know the transition width. Based on the transition width, select the value of the order of the filter. Okay, that's how we have to do. Then the next one is the Bartlett window. Bartlett window. This gives a transition width of 8 pi by m, and a stop band attenuation of minus 25. Then Hanning window also gives 8 pi by m and a stop band attenuation of minus 44. Okay. Then Hamming window also gives 8 pi by m, but a stop band attenuation of minus 53 decibels. Blackman window is not specified in your syllabus, but I suggest it's better you write it down, because like it's a part of the different windows that we usually discuss. Okay, so it's better you have it. So even though it's not there, it's better to learn something extra. So that is the Blackman window. Okay. So is the procedure clear? I will just repeat once again. The filter specification or the filter design problem that will be given to you is, it will tell you whether it's a low pass, high pass or a band pass filter. They will give you the cutoff frequency omega c, or they could specify omega s and omega p. From that we can find out omega c. Omega c will be at the center of the transition band, omega c. I will give you that as a part of the steps. And then the stop band attenuation delta s, delta p will be given to you. The decibel range also can be given. So using delta s, find 20 log of delta s, you will get a decibels. Okay, you will get a decibels value. Then you will have to select the window. So exactly it might not match your AS, but select a window which much exceeds the 20 dB delta S value. Okay, 20 dB delta S value. Let it select a window which is more than that value. Once you select a particular window, now say for example Hamming, then you know the transition width of that particular Hamming window. You will have to take this only, delta W. You know the transition width, so find the value of M. Okay, once you know the value of M, you can write down the equation for this particular window. Every window has a different equation. Rectangular window is simple. It is just 1 in the limit 0 to m minus 1. But the other windows have an equation. Okay, so you'll have to write down the equation of the window function, and then go back to this step, that is what? To find HD of n. To find HD of n, correct? HD of omega is this low pass filter. Find HD of n with this process of integration. Now here we have already performed the integration, and you know the value of HD of n. Okay. So now since we'll be solving lot of problems, you can just use this equation of HD of n in the problems. But in the exam, what you do is you derive this equation of HD of n. Is that clear what I'm telling you? Since I've already derived the equation of HD of n, I'll just use the equation of HD of n in the problems to solve. But in the exam, you'll have to derive this HD of n for a filter design problem, because that will be only one problem that you'll be solving in the test or exam. So you'll have to derive this equation for HD of n there. So you know the window function, you know the equation for HD of n, multiply the on substituting the values of n and multiply h of n, multiply HD of n and W of n. So what do you get? You're going to get your h of n, that is the filter coefficients. So that is the overall procedure for an FIR filter. Next, what we have to do is, before taking up the design procedure and the problems, let us write down the equations for these different window functions. Okay, because you need the equations in the filter design, right? So we'll have to write down the equations for the different filters. And this is also one question which is generally asked in the exam. That is, what are the different kinds of windows used for the FIR filter design? Write its equation and the frequency response of the window function. Okay, is asked as a part of the theory question. Okay. So shall we do that? You want to copy this down? I'll just pause it for some time. So this order M, sometimes even capital N is used in place of M. It's one and the same. We don't have to get confused with that. So for these windows, let us write down the expressions or the equations for the window functions, which will be useful for the design problems. Do that. So the different kinds of window functions and its equations. Types of window functions. Rectangular, you already know how the what is the equation, and then how the waveform looks like. Let's go ahead with the Bartlett window. Okay. So Bartlett window, an endpoint Bartlett window is given as, we denote as rectangle but b of n. The equation is 1 minus 2 magnitude of n minus of m minus 1 by 2 divided by n minus 1 in the interval 0 to n minus 1 and 0 otherwise. So how does a Bartlett window look like? Is a Bartlett window has a triangular shape. It has a triangular shape. So now the rectangular window that we have, it is like suddenly we are stopping those the remaining samples that we have in HD of n, or we are truncating those values in HD of n. So this results in ripples in the passband and the stopband, which is called as the Gibbs phenomenon, which I had told you before. Okay, it's called as the Gibbs phenomenon. So it is observed that some of these ripples to a certain extent can be reduced if you have a tapering window. Instead of having that flat rectangular window, if you have a tapering window, then it is seen that the attenuation, the ripples are going to be much lesser. Okay, or the Gibbs phenomenon would be much lesser if that is the case. So that is the reason these different windows are taken. So this has a triangular shape, starts at 0, ends at m minus 1. It is discrete, right? So I am writing the samples like this. Like this. It is symmetric about the midpoint, m minus 1 by 2. Symmetric about the midpoint. And usually we take an odd filter, that is odd order filter, that is the value of m. We usually take an odd value because your value of alpha is m minus 1 by 2, right? So we want alpha to be an integer. So that's the reason generally we take m to be odd value. We can odd value. That is Bartlett window, and every window has a frequency response. The sinc function that we obtained for the rectangular window, like that, every window will have a frequency response. So along with the window function, this is in time domain, right? Along with the window function, you'll have to also plot the frequency response when the theory question is asked. And you can refer notes for that and just plot it. I will not do it here. I will just show you the different kinds of windows. So compared to the rectangular window, this Bartlett window gives a generally a smooth magnitude response. Okay, but the problem is this creates a little wider transition region. Creates a little wider transition region. That is Bartlett window. The equation is important because you will have to use it in the design procedure. Sorry, this is m minus. I used m. M minus 1. Shall we go to the next one? Next is Hamming window. Hamming window. So that is denoted as WHAM of n. Hamming window. The equation of this is 0.54 minus 0.46 cos of 2 pi n by m minus 1 between the interval 0 to m minus 1, and it is 0 otherwise. 0 otherwise. So in the design problem, you'll have to substitute the values of n and find out these values of the window function and the HD of n. Actually, the computations are lots in the filter design problem. The procedure, once you understand for one or two problems, the procedure will not change, but the calculations, the amount of calculations that you have to do, that is more for a filter design problem. Okay. So this Hamming window has a bell shape. The Hamming window has a bell shape with a non-zero initial and last value. So something like a Gaussian shape. Okay, so this value is non-zero, the first and last value at m minus 1. Okay, otherwise it is a symmetric bell-shaped window like this. That's a Hamming window. The first and last values are not zeros. For a Hamming window. So this window is generally found to be used in speech processing. More in speech processing applications, they make use of this window. That's the Hamming window. So all these equations, like I told you, has to be remembered. Then the next window is the Hamming window. Okay. Next window is the Hamming window. H-A-N-N-I-N-G. Hamming window denoted as WHAN of n. The equation is 0.5 minus 0.5 cos of 2 pi n by m minus 1, 0 less than or equal to n less than or equal to m minus 1, and it is 0 otherwise. Okay. So Hamming window also has a bell shape. This is also bell shape or Gaussian shape, but the first and the last values are zeros. The first and the last values are zeros. M minus 1. Okay, bell shaped with the first and last value 0. That's a Hamming window. The equation is this. So this is also used in speech and music processing and spectrum analysis. Okay, in such cases, such applications, we make use of this window. Okay. The last one, that is the Blackman. I'll just give you the equation of Blackman and also how the window looks like. Just keep it in mind. Though it's not mentioned in your syllabus as such, I thought it's better you write it down as it's a part of all the windows that we discuss. Okay. So Blackman window. Blackman window. The equation is WBL of n 0.42 minus 0.5 cos 2 pi n by m minus 1 plus 0.08 cos 4 pi n by m minus 1. Okay, in the interval 0 to m minus 1 and 0 in other places. So this is very similar to Hamming and Hanning and has a bell shaped again. Okay, only differences you see in the equation of the different windows. 0 to m minus 1, that is the Blackman window. Okay. So like I told you, these window functions, they ask you as a theory question also. Describe the different kinds of windows used in the FIR filter design. So you'll have to write all these window functions and also you have to write the frequency response. Like I told you, I have not drawn the frequency response here, but it's there in the notes and in the textbooks as well. Just follow that and write down the responses for all the windows as well. Okay. So that's the explanation. That is how we design or the overall gist of how the FIR filter is designed. Now what we can do is, let's write down the design procedure in proper steps. Okay, so if you follow this design procedure for any filter that is given to you, okay, we can use this. So you have a proper steps, what you have to do one after the other. So we'll write the steps in the design procedure today. I'll take up problems in the next class. Okay, so let's write down the steps in the design procedure. So all this that we discussed till now will be covered in the design procedure. See, theory questions I've kept on repeating in DSP is important. So they could ask you the design procedure also. You cannot rule out any question in DSP. So what will be given to you first is omega P, omega S, delta P, delta S. Passband edge frequency, stop band edge frequency, passband ripple, stop band ripple will be given to you. And the kind of filter they will tell you. Okay, low pass or high pass or band pass. We'll write the procedure for low pass. Same thing, you can extend it to other filters. So first find 20 log delta S. 20 log delta S, that is in decibels. You'll get a negative value. Okay, because ripple is usually 0.1, it will be a fraction, the ripple. That's why you get a negative value for this 20 log delta S. Denote this as AS. Denote this as AS. Stop band attenuation in decibels. Stop band attenuation in decibels. So this is the specifications, the filter specifications that will be given to you in the problem. Okay, so first step, what you have to do first, select the window. You have to first select the window. So the table which I gave you previously, look at that table, select the window such that the stop band attenuation that is specified in the table, right, exceeds your AS value. So select a window whose stopband attenuation is more than the AS that is given to you in the problem. Once you select the window, you know what is the transition width, right? You know what is the transition width for the corresponding window that we have written it down. So you can find M. Find M so that it is more than or equal to K into 2 pi by delta omega. Why have I written it like this? Because what is given to you in that table is delta omega, which will be some number like 8 pi by 8 pi m. It is 8 pi by m. For another window, it is 12 pi by m. For another window, it is 4 pi by m. So it's a multiple of 2 pi. That's why we have written here as k. But you just take this value which is in the table. So if it's 8 pi by m, what is your m equal to? 8 pi by delta omega, because you know delta omega. What is delta omega? Omega s minus omega p. Omega s minus omega p. That is delta omega. So can you find m? We can find m. So usually we round off m to the next highest value, or we just keep it odd. The next highest odd integer. We don't deal here with fractions because they are all discrete values. So your order also should be an integer. So round off m to the next highest odd value. Next highest odd value. Okay, why odd? Because so that your alpha value also is an integer. Alpha is m minus 1 by 2, so that is also an integer. Okay. So once you have found out the order of the filter, then start with the next step will be HD of omega, the desired frequency response of the filter. So this I am writing for low pass. So if it is high pass, this will change. E power minus j omega alpha for magnitude of omega less than omega c, and 0 for omega c less than magnitude of omega less than pi, which we have written. Less than or equal to, you can take. So this is the ideal frequency response HD of omega, which we have to start off with, right? Then find HD of n. Like I told you, all that integration process you will have to do when you're doing it in the test or exam, because there you'll be solving only one problem. But in the class when we are doing, we'll just use this value of HD of n, which we derived just now. N equals alpha. This we have derived just now. So HD of n you're going to write down. Okay, using HD of omega. Then we don't know omega c, correct? Because omega c is, sometimes they give you omega c directly in the problem, sometimes they don't. So if they have not given you omega c, find omega c as omega p plus delta omega by 2. Center of the transition band. Center of the transition band will be your cutoff frequency, omega c. Because omega c is required for here in this equation you need, right? So that is why you should find omega c. And alpha you need. What is alpha? As we had discussed before, it's m minus 1 by 2. Alpha is m minus 1 by 2 to maintain symmetry. So in this equation of HD of n, now you know omega c and you know the value of alpha. Finally, write down the equation h of n equals HD of n into W of n. W of n is the window function, which you know the equation for now depending on the kind of window. So you know W of n, you know HD of n, multiply the corresponding samples. You'll have to substitute the values of n from 0 to m minus 1 and find h of n values. Find h of n values, that is the filter coefficients that we had to design. Okay. So that is the entire design procedure, what all we discussed till now, listed in the form of steps. We just have to use this to solve the problems.